Hello, students. This is Mr. Sharan coming into you to discuss Unit 5 Project Quantum Mechanics. I'd received a number of questions recently regarding one of the parts of this that isn't really clearly explained on how to do. So this short video is going to be a quick explanation on how to gather the information, or the data I should say specifically, for the Unit 5 project on quantum mechanics, specifically Lesson 23. So, on the screen currently is what you should see as the bucket for this. I'm going to scroll down, so we're going to go to Lesson 23 question. So here we are on quantum mechanics, Lesson 23, and we are attempting to fill out this data table here. Let me just give you a little bit of a setup of what we're looking for in this data table. We are testing three different metals: potassium, calcium, and uranium. And we're testing them for their photoelectric effect, which is when photons are of different wavelengths, so different energies, are fired at a plate of this pure element. What is the energy of the electrons that are ejected from that? Now, we're going to be testing three different wavelengths of light at a 50 nanometer difference: 200 nanometer, 250, and 300 nanometers, and three different elements. So we have really two independent sets of independent variables. One set of independent variables being your actual element itself, the other set of independent variables being your wavelengths of light. We're then going to record at what voltage, what's voltage, the minimum voltage that you can resist those electrons ejected by them, and what's the actual voltage value. So I'm going to show you how to set up, and I'm going to show you how to collect one of the three columns of data, and then you will be responsible for collecting the rest as part of the completion of this project. So without further ado, let's take that on. So here's what the simulator should look like when set up properly. Couple of things you should do: make sure that you've set the show voltage gradient. This is a good visual. So what's happened here is the voltage gradient is telling me that there's an electromagnetic field, electrical field specifically, between this plate and this plate within this device. And the arrows show the force lines, the force field lines. So any object that's electrically charged that enters this will react as if being pushed by these field lines. Now what we want to see is what's the level of energy needed, the minimum level of energy needed by this electron to overcome this field to make it all the way to the other plate to activate this light. This will tell us how much energy the photons had going in as they convert it to this. We'll also see how different metals that are basically being used in this conductive photoelectric cell produce different energy thresholds. So I'm going to start at the top, so the first column. So I'm going to do 300. So I'm going to set my wavelengths to 300. I'm going to keep the intensity at 50%. Actually, sorry, let's make it to 100%. So we're going to do the intensity at 100%, and then I'm going to grade this voltage to see. So let's just show you what I mean. Flash, and we see at a 4 voltage eVolt. So there's a 4-volt field pushing electrons this way. It's too much. The electrons can't make it. So I'm going to reduce it by half. Alright, and I'm going to go now. Alright. Okay, so 2 volts, still not enough. Okay, so 4 volts got pushed back, 2 volts, so I've reduced the field strength, still pushes back. Let's go further down. I'm going to go down to 1 volt. Alright, so 1 volt was enough to... So 1 volt, in a 1 volt field, the electrons have enough energy to make it to the other plate to activate the light bulb. Now, we want to know what the minimum is, or what is the minimum voltage field that you can be in here and still light the light. So I'm going to now, we know it's less than 2 and it is either 1 or greater than 1. We need to find out exactly to the single decimal. So at this point, I'm just going to increment up. So 1.1 still works. 1.2 still works. 1.3. 1.4. 1.5. 1.6, getting close to it. 7. 1.8. Oh. 9. And there we go. So 1.8. So going back to my original, I would say 1.8 EV. Alright, so for potassium, at 300 nanometers, 100% intensity beam, I need the electrons emitted have an electron voltage of 1.8 volts. So let's now see what happens when we do calcium. Alright, so let's change this to calcium. Max it out again. I'm going to once again do the same thing. 100% intensity. I fire the beam. Ooh, really doesn't make it that far. So let's go down to 2 again. Half it. Flashlight. Get further, but not quite. Let's go down further to 1. Flashlight. Oh, much closer. Alright, so once again, it's between 1 and 2. So let's go 1.1. 1.2. 1.3. Now remember, we're seeing at what voltage does it not make it? 1.3. So, going back to fill in, 2 E volts is the voltage, the maximum voltage of electrons coming off of the calcium plate due to the photoelectric effect. Let's do our last one. So, uranium. Once again, max it out. Everything else. Bang. So 4 was too intense. Let's go down to 2. Oh, 2 still not getting a lot. Let's go down to 1. So look, so 1 only got us about halfway. 4 was, barely got to here. 2 got to here. 1's getting us halfway. Let's try 1.5. Okay, so 1.5. Let's try 1.6. And there we go, 1.5. So, final point, or sign at 1.5, 0.5 evolts. Okay, so what we can see is at the at the longer wavelength, photons from potassium to uranium, the electrical potential of the emitted electrons decreases. Potassium has the highest energy, so if I were making a photovoltaic cell in this first round of experiments, it seems like potassium would be the better one to use because for the long wavelength lights, it produces high energy electrons. All right, so that's the basics of how to collect this. You'll repeat the patterns here and here, except this time you're going to use 250 nanometers and 200 nanometers. And once you have a complete set of data, you'll go on to the next question about what patterns you're looking. Remember, what patterns we're looking for is when you change this, so when you change the element, how is the electron voltage affected? When you change the wavelength, how is the electron voltage affected? How do these two changes together give us a pattern? So if you think of it this way as like, what's the pattern when you go this way? What's the pattern when you go left to right? And what's the pattern when you go diagonal with these? So what would be the pattern when you go diagonal with these? All right. Hopefully that'll help you with this section of the project. Um, if you want more videos like this, please submit questions to me, and I'll be happy to record additional responses.